Hi everybody, in this video we are going to go over an example of nodal analysis. Okay, so here is the circuit. We are going to solve for the voltages at nodes V1, V2, and V3. So the first step, as always with nodal analysis, is to assign names to the nodes, which we've already done. Step 2 is to assign the current directions at each node, and you can do that arbitrarily as long as you're consistent. So for example, if I say the current with respect to this branch here is going upward, then it must be going in this direction here, and it must be coming downward into V1. So I'll get rid of this one. So this here is an example of being consistent with your directions of your current with respect to a specific branch. So now for this one, I can say it goes downward, here I can say it goes to the right, here I can say it goes to the right, here I can say it goes downward, here I can also say it goes downward. I'm going to give all these currents names. I'm going to use a slightly different color here, I1, I2, I3, I4, I5, I6, I7. Now notice that I6 and I1 are actually the same current. This green arrow is the same exact current as this green arrow here. So I'm actually going to just get rid of I6 right off the bat, and I'm going to write in I1 instead, just to keep things simple for myself in the long run. So now I'll go ahead and write in my KCL equations at each node. So with respect to the V1 node, I1 goes into there. Coming out of there is I2 plus I3. So now I'm just going to translate this into the node voltages. So I1 is going to be equal to V3 minus V1 divided by 6. Let's write that out. V3 minus V1 divided by 6. So you can read this as starting at node V3, going toward V1 through the 6 ohm resistor. So think of that minus sign as an arrow from V3 toward V1 across the 6 ohm resistor. So there's I1, and then I2 can be similarly written as V1 minus 0 for ground, divided by 2, and then we have the plus I3. Well, I3 we don't have an expression for, because there's no resistor that's connected to I3. So we'll leave that for later. Let's do nodal analysis now at V2, node V2. So we have, from V2 we have I3 going into the node. Leaving the node we have I4 and we have I5. So we'll do the same thing now and convert this to voltages right away. So I3, again, we don't know what that is, so we're going to leave that as I3. I4 is V2 over 4 ohm resistor, and then we have I5, which we don't know, because again, similarly to I3, there's no resistor here. So we leave that as I5. So now we move on to V3. So with respect to V3, I5 is going into V3, and leaving V3 is the sum of I1 and I7. So I5, we don't know, we'll leave that as is. I1 is, what is that? I1 is V3 minus V1 over 6, which we actually wrote already up here. So V3, let's erase that. So we have we have V3 minus V1 over 6, and then plus I7, and I7 is just V3 over 3. So plus V3 over 3. So let's take a look, tally up the number of unknowns. So we have V1, we have I3, we have V3. This I3 I'm not going to highlight again because we already got it here. We have V2, we have I5, V3 we already have, I5 we already have, V1 we already have, V3 we already have. So there are a total of 3 equations so far and 5 unknowns. All the unknowns are highlighted, so we need 2 more equations. And we're going to get those equations from these voltage sources that are here. The nice thing about voltage sources is that they guarantee a relationship between nodes. In this case, with respect to this 25 volt source, what it's saying is that if you start here from V2 and then make your way over to V1, you're going to experience a voltage gain of plus 25 volts. So let's write that out as an expression. Okay, so we have V1 is equal to whatever V2 is plus 25. And so that's cool. Now we're going to do the same thing but with this dependent voltage source here. So you can see that this is a current dependent voltage source because this depends on the current going through this 2 ohm resistor as illustrated by this downward facing red arrow here. And the scalar or the amplification is 5. So what it's saying is, so really let's write this out. The way you would see this in the textbook is 5 times I2. So you can write this out as an expression now, saying that V3 is equal to whatever V2 is plus this amount. So V3 is equal to V2 plus 5 times I2. So now we have 2 extra equations, and I think that's how many more we wanted when we tallied up our number of unknowns a second ago. So let's see if we can move this downstairs. Okay, here it is. Okay. So we now have 5 equations. How many unknowns do we have? Did we introduce any new unknowns? So let's see. We had. Hang on a second. Before we move forward, always do this step similarly to what we had done earlier. Translate from your currents. So if you this I2, translate it to a voltage first, so we don't get confused. So let's take care of that. So this here is really, I'm going to rewrite this. It's saying V3 is equal to V2 plus 5 times whatever I2 is, and we found that I2 is equal to V1 divided by 2. So I write that in. So I'm going to scoot this off to the side, and I'm going to look at this instead. So now I have 5 equations. With respect to these 3 up here, we've already highlighted all of the unknowns, the variables that we've, all the unique variables have already been highlighted. We're going to do the same thing now for these remaining 2 equations down here. So V1 has already been highlighted right here. V2 has already been highlighted right there. 25 is a known. The V3 has been highlighted already up there. The V2 is right here. The V1 we already have as well. So no new unknowns were introduced, which is good. Because now if you look at this, what we have, what we have are 5 equations, 5 unknowns. So what that means is we have everything we need in order to solve this system and to solve for all of these unknown variables that are highlighted in yellow here. So for this final step here, we're not going to go through the algebra. We're going to do it, crunch it on MATLAB, make it a little easier for ourselves. But I want to point out something real quick. These are called supernodes. That's how you'll be introduced to them in your textbook. The idea is essentially we call them a supernode because there were these currents in here that we couldn't quantify, as you saw earlier, I3 and I5. So another way of approaching this, and you can refer to your textbook for this method, is where you look at this whole thing up here that I'm boxing up or dashing around. You look at that whole thing as a node. So really, I3 and I5 won't show up if you do this in a different method, which again I'll leave for you to explore by looking into your textbook. For now, we're going to finish up this problem, and we're going to skip the menial math